David Quig received a PhD in nutritional biochemistry from the University of Illinois, served as a senior cardiovascular pharmacologist for 7 years. For the past 11 years, he served as vice president for scientific support for Doctors Data, where he's focused on toxic metals, facilitated and published an array of studies spanning metal detoxification for autistic children to the poisoning of our environment with amalgam-derived mercury. And it's my pleasure to introduce Dr. David Quig.
Good morning. It's a wonderful pleasure to be back here. I haven't been here for about 8 years now. And I'm supposed to read this little card, but my old eyes can't quite say it. Basically, it's a disclosure that I do work for a commercial laboratory. However, I'm not going to be promoting any products or anything like that. I will show data that was attained using that laboratory. When I first started 11 years ago in this industry, I always feared having to speak after Dr. Boyd Haley. It was just, most people do. It's almost as bad as speaking after Dr. Kennedy, who has people rolling in the aisles. But over the years, Dr. Haley and I have come to collaborate on a lot of issues intellectually, and we were even part of an email group called the Rational Thinkers. And recently we were talking about what happened. We no longer get any emails from this Rational Thinker group, and neither one of us knows what happened to the group. And I think we've been stymied by somebody with higher powers. So I'm not afraid to talk after Dr. Haley anymore, because there's so much of what he said will dovetail into what I'm presenting. And so what I'd like to do today is talk first about the results of an original research study that we did with fecal mercury as it contributes to environmental mercury pollution, that being derived from the amalgams to start with. And then address basic metal toxicology. I know I'm speaking to the choir here, but I know there's new members. And I've been asked to speak about the rationale for appropriate laboratory testing, and I'm going to emphasize the difference between testing for exposure versus net retention. Then I'll further address the efficiency of currently available metal detox agents and follow up on Boyd's comment about EDTA and mercury, and then finally address a couple of topics related to mercury detoxification, including selenium, intravenous reduced glutathione, and chlorella. So let's start with this vicious cycling of mercury from the teeth to the environment and back to the body. Now, what am I talking about here? Over the past decade or so, the use of mercury in the United States has declined sharply. Its use in medical devices has decreased, or mercury battery. The elimination of mercury in paint, which it's really hard to tell how complete that is. But importantly, the conversion or closure of chemical plants with mercury electrolyte cells, chloralkali plants. So a lot of them have been closed. However, there are 8 remaining plants that contain about 2,400 metric tons of mercury. And those plants are scheduled for closure and or conversion. But the problem is, what do we do with 24 metric tons of mercury? It's extremely expensive to safely dispose of mercury, and I'm not sure that it's even really possible. Certainly in the short term, you could lock it up in some huge cement vault underground, but eventually it's going to get back to us. And the mercury that I talked about at these chloralkali plants is worth about $45 million. So you think we're just going to put it in the ground and hide it? Or you think we're going to go for the $45 million? There have been moves to prohibit the sale of this mercury to other countries. That used to be a great income for some individuals. But the problem is, prohibiting the sales increases the street value of mercury and makes mining of more mercury even more lucrative. And if you think I'm joking when I talk about the street value of mercury, one of my colleagues, he's an analytical chemist, and he's, you know, that 10th decimal place guy. He is also an eBay fanatic, and he has found people selling mercury on eBay. You say, what the hell are they going to do with this mercury when you buy it? It's got to be expensive to ship. This stuff is so heavy. But there are certain cults or subcultures where they actually use mercury. Some believe that it has sex-enhancing powers for males. And in fact, locally here in the Chicago area, we had to deal with a case. We worked with an occupational medical doctor who had a young woman who actually received an intravenous dose of elemental mercury. And I don't even know how you could push that through a syringe. Her unprovoked urine mercury level when they sent us the 24-hour urine collection was 20,000 micrograms of mercury in 24 hours. We did a variety of tests for them and did in fact demonstrate that that inorganic mercury was partitioned, the vast majority in the serum fraction bound to albumin and nonspecific proteins as opposed to the red cell. And they actually had x-rays of this young girl, and you could see mercury deposits in different parts of her body, especially her kidneys. The doc was terrified to try to do anything to detoxify her, to mobilize, even to try to get it out of the blood. And I must admit it was a pretty futile case, and she did die shortly thereafter. So it's no joke when I talk about the street value of mercury. Now, as a lead-in to our study of why we were looking at fecal mercury, we need to think about pharmaceutical versus natural detoxification. Pharmaceutical detox of metals binds the agents or chelators, bind the metals, trap them, translocate them for excretion, the vast majority of which go through the kidneys, which isn't the greatest idea, but all these compounds are water-soluble, and this is what we have currently. This is in sharp contrast to natural detoxification, as Dr. Haley just pointed out, where you have glutathione, intracellular glutathione, binding to metals like mercury, cadmium, lead, translocating those metals to the extracellular space where the majority get excreted in the bile. So we have this biliary excretion of metals as opposed to urinary with the natural detox process. We also looked at some data from some published studies that clearly showed that there are much higher levels of mercury in the tongue and gingiva in people with amalgams, up to 4.2 micrograms per gram of cell. That's 4.2 parts per million. And also, if one looks at desquamated oral mucosal cells, or just take scrapings, even in cells that are not directly adjacent to an amalgam filling, the level of mercury in those cells, in that mouth, is about 10 times higher than cells taken from someone's mouth who never had or doesn't have any amalgams. So 10 times as much mercury in the oral cavity in cells that aren't even in direct contact. But this stuff is inert, so the magic act is how it gets from the amalgam into those cells. So we did a study where we started to investigate what the relationship between amalgams in the mouth was related to this biliary or fecal mercury concentration. And we had a questionnaire where we asked some basic questions about are there amalgams present, how many, if you've had them, how long ago has it been since they've been removed, the number and the age of amalgams, which has a significant impact on off-gassing, and also because there is such a strong contribution by seafood with organic mercury, we asked about the potential confounding factor of seafood consumption, the frequency and quantity, and other potential exposures that might exist. Now here is shown the fecal mercury concentration on the y-axis, plotted against whether or not people had amalgams, whether they were removed or if they never had them. And looking at 1,400 observations of people with amalgams, the concentration of mercury in a stool specimen was 10 times higher than in an individual that had no amalgams. There was a group that had amalgams and had them removed, and they were somewhat intermediate, but there's, it's hard to say. There's different times since the removal. So the point of this slide is we've got 10 times more mercury in the cells in the mouth. We've got 10 times more mercury in the feces in people that have amalgams in place, keeping in mind that it's inert. Now there's this other interesting group where people just said no, and there were 1,000 people that said no. And last night when I was looking at this slide, I thought, how do I explain this if somebody asked me? We've got, do you have amalgams? Yes. Did you have them removed? Yes, I had them removed. Or no, I never had them. How can you just say no? One of my colleagues is a board-certified psychiatrist, and I think he put this question in here to try to fool people. And it'd be interesting to go back and evaluate the mercury levels in these people, these 1,000 people that didn't quite know how to answer this question. It's really not that complicated. And then we did, we tried to see if there was a direct correlation between the fecal mercury and the number of amalgam surfaces. And you can see that there is a nice, basically linear relationship between the number of amalgams and the level of mercury in the feces. Now, to eliminate the confounding variable of seafood consumption, the methylmercury, particularly in the larger fish, we evaluated the levels of fecal mercury compared to the frequency of fish consumption. And there was a relationship between fish consumption and fecal mercury. However, note that even in the highest group, what I would call the high-end fish consumers, more than 36 ounces per month, the level of mercury in their feces was only about equal to a person that had 1 or 2 amalgams. Now you say, does that mean that the mercury from fish is okay? It didn't appear in their feces? No. The mercury in fish, methylmercury, is about 95% absorbed. So it doesn't come out telltale in the feces or in the bile directly, but rather it's being absorbed. But we did have to rule out the contribution because we were addressing specifically what contribution the amalgams had. Then we did some calculations to see what the total amount of mercury in the U.S. population being released to our water treatment facilities was on an annual basis. And using a rough estimate of total fecal output per day, we came up with 40 microgram of mercury per amalgam-bearing person per day. That translated to 15 milligram per person per year, which came to a total, if we assume 210 million people with amalgams, of 3.4 tons of mercury put into the environment annually due to the placement of amalgams in people's mouths. This isn't accounting for the waste coming out of the dental office or what's being eliminated as waste. This is strictly what is being put into our environment. 3.4 tons coming from people's mouths. Again, it's inert though. So there was another study that was done in Sweden. They only looked at about 10 individuals and found very, very similar results, about 0.4 or about 0.5 microgram per gram mercury in the feces when amalgams were present, with 13 amalgams. Daily excretion of about 60 micrograms. We used 40 micrograms. And interestingly, they speciated that mercury, and it was found to be about 99% inorganic and not methyl or organic. So we have the issue of, even if there is methylation of amalgam-derived mercury in the mouth by yeast or bacteria, that mercury is very likely to be absorbed and taken up into the body. So primarily what we're looking at in the feces is, in fact, inorganic mercury. Now, this is a study where they showed a time course of fecal mercury from the same group from Sweden over time after removal of amalgams. And this is without using a rubber dam. And they didn't really describe the procedure, so I assume they just drilled the stuff out and yanked it out. Now, the controls had very similar levels. These are in units that are 1,000-fold different, so 0.05 for the controls, which is exactly what we found. The amalgam group had a basal level of 0.54, or 100 times higher. And then 2 days after removal, without a rubber dam, the level of mercury in the feces, which is no doubt in large part particulate from the extraction, increased to about 56,000. And then 14 days later, as the bowels were moving, the intestine was being cleared, it started to drop. But even 2 months out, it was significantly higher than those who never had amalgams. Now, one really important thing, if you ever submit a fecal specimen to a laboratory for analysis of mercury, don't do it right after amalgam removal. My 10th decimal place guy did in fact do that. He came from the dentist, he collected his stool specimen, and he nearly blew up our ICP-MS. Had to shut it down, retube it, and clean it out because his levels were up around 40, was about 40,000. So, huge amount. And then again, this is without the rubber dam. It'd be interesting to compare with and without. So what is the fate of this fecal mercury? Some people would say, oh, well, it's just passing through the system. But Boyd just told you about the matrix metalloprotein. So this mercury passing through is going to have a localized effect in the gut, as Boyd addressed the specifics of it. So while it is a transient exposure there, it could be very significant. But what happens with this fecal mercury, it gets sent to the water treatment facility. The solids get dried as the sewage sludge gets dried. And this contains, obviously, the biliary excrement, which also contains dioxins, cadmium, and other toxic chemicals and metals. And as well as that, not only coming from the bile by the natural route, but that coming from the desquamated mucosal cells and swallowed on a daily basis. Now, I should add that what I didn't show you was that in that correlation between a number of amalgams and fecal mercury, we studied certain individuals who had mercury at the time in their mouth, and on 14 separate fecal collections, there was only about 15% variability in the mercury concentration. So it's incredibly constant from day to day. In fact, some dentists will even use a fecal mercury analysis to show people that that mercury in their mouth is not just staying in their mouth, it is ending up in the feces. So, can have that utility as well. Now, these dried human sludge, this dried human feces, is turned into a PC term called biosolids. Biosolids, even pelleted and packaged and sold as fertilizer. Or it could be burned. Because what a great way to get rid of mercury. You burn it. It's volatile at room temperature. You burn it, it's gone. It's all gone, just like the mercury in the blood. It's gone. It's not a problem anymore. Not a good idea. But it is a legal practice in this country to take this massive amounts of biosolids and use it as fertilizers on our crops and pastures. So essentially, we are recycling that mercury from your neighbor's amalgam's mouth onto our crops, back in the food supply, back into you. And I'm very, very much pro-recycling, but not when I'm the filter. Okay? That's not going to happen. It's not a good idea. So we have this dried human sludge containing a lot of mercury and other toxins, and we can burn it. And like I said, we can burn those biosolids, and they're gone from the place where you burn them. but obviously they're going to get into the atmosphere, come back into the ecosystem, become methylated, and work its way up the food chain. On the other hand, if we use it for fertilizer, it can have direct runoff into our ponds, streams, lakes, and rivers, or be taken up by the crops or livestock and again get back into the system. So we have this terrible cycling of mercury from the amalgams in the mouth back into the environment, into the food chain, into the water, and into the air. Now I want to switch gears a bit and just talk about basic toxicology. You're all aware that one of the primary rules, the first rule of toxicology, is remove the source of exposure. And there was a really interesting case that I had to consult with. There was a woman, she was a 59-year-old homemaker and had an inexplicable progressive neuropathy. Her husband was an accountant, so there was no real occupational exposure to metals or necessarily chemicals. And she was seen by many different ologists and had all kinds of scans and tests, and they couldn't figure out what was wrong with her, why she had this, not only neuropathy, but progressive neuropathy. Fortunately, one of her neighbors was an environmental medicine doc, and the first thing he thought of was toxic metals because they couldn't find anything else on their traditional testing. So he actually did a provocation challenge using a preload of 40 mg per kilogram glycine, and I'll talk more about that, and a rather low dose of DMSA, around 10 mg per kilogram. Most people are using in the ballpark of 20 to 30 milligram per kilogram. And lo and behold, when they looked at her urine metals, there was a significant amount of mercury, about 29, which isn't terribly high. I've seen much, much higher levels than that. But quite a bit of lead and quite a bit of antimony. Okay, so she's a housewife. Her husband's an accountant. Where is this coming from? They had their water tested. They had the paint in their house tested. They did live on the East Coast, and we knew where a lot of the mercury was coming from their frequent seafood consumption. But the lead and the antimony were a real mystery. It wasn't in the water. And finally, the woman fessed up to the fact that she did drink quite a bit of wine. So the EM doc had the wine tested at an EPA-certified lab. And lo and behold, the wine contained levels of lead and antimony that were 3 and 11 times respectively higher than the maximal contamination limit for drinking water. She bought this stuff with 3 and 11 times higher the levels of lead and antimony. Now, since this is being taped, I can't mention the name of the wine, but the important point is that this was really high-quality wine in a box. And what is wine in a box? It's wine in a bag. And antimony is used extensively in plastics chemistry as a cross-linking agent. So you have this acidic alcoholic beverage soaking in a bag that's loaded with antimony. Where the lead came from, I can't tell you, but it was in fact in the wine. They really ought to sell this stuff by the pound because it's so heavy. Now, I mentioned the glycine assisting agent, and we don't know the precise mechanisms for how this works, but we've seen time and time again that if one gives about 40 mg per kilogram glycine orally, about 2 hours before a challenge with DMSA, DMPS, or EDTA for that matter, we see a substantial increase in the output of metals. And this converts to about 3 to 4 grams of glycine for your average size adult. And glycine is actually very palatable. It's like glutamine. It's just very, very so slightly sweet. So many amino acids are terribly bitter. So it's easy to mix with water, have the patient drink it, and then give the DMSA and collect the urine for 6 hours. It should be used in conjunction with an agent and not alone, because apparently one thing that's happening is the glycine has a very weak but significant enough affinity for metals and it does enter the cells. Remember, none of these agents get inside of cells normally. So the glycine can shuttle into the cell, weakly bind loosely available metals, and then just come right back out of the cell where it would meet up with DMSA or DMPS, which has a much higher affinity for the metal, take it away from the glycine and shuttle it out in the kidneys, or through the urine rather. It should not be used alone because we would have a ping pong effect. And the published studies on this are most impressive or depressive with respect to aluminum, where the glycine has a high affinity. The glycine can go in a cell, pick up affinity, or pick up, say, aluminum, and then just ping-pong it around the body without a high, irreversible fractional rate of excretion. So you always want to couple it with an agent that has a higher affinity. There may be some other mechanisms by which the glycine is working, but this is the working hypothesis. It is contraindicated if people have hyperammonemia, because you don't want to give them an excess of any amino acid. It may exacerbate psychoses in some psychiatric individuals. And you wouldn't want to use it on a chronic basis for detoxification because large amounts of glycine could be converted to oxalate, and you could get calcium oxalate stone formation. So pretty much people are using it as a facilitating agent strictly for the challenge, not for routine treatment. Now, the whole concept of chronic metal toxicity fits the criteria, the basic tenets of toxicology. That is, we have exposure, assimilation, some degree of retention, and possibly toxicity. With acute poisoning, we obviously have all this going on, but with chronic metal toxicity, it's not considered to be a reality, despite the fact that we have exposure, assimilation, retention, and these remotely associated symptoms that are coincidentally related to that mercury or lead or cadmium retention. So it's not generally accepted as requiring treatment. It is, however, and has its own term, and the oxymoron for this is subclinical metal toxicity. Subclinical. It's subclinical. Why are they at the clinic? Okay? The oxymoron of the decade. And really what they mean by subclinical is subthreshold poisoning. It doesn't meet the criteria. For example, if you submit a urine specimen, unprovoked urine specimen, to one of the large labs in the Midwest that has tremendous accolades and is well respected, they have a cutoff value for urine mercury of 50 micrograms per gram creatinine. Below 50 microgram per gram creatinine, you're considered okay. 50 micro, and again, it gets back to this threshold value. And it's the logic, again, that at 50 microgram per gram creatinine, 100% of individuals will have some sort of neurological deficit. So therefore, that's the level that we consider. This is not consistent at all with preventive medicine, nor scientific logic, for that matter. So what we really need to talk about is this net retention versus exposure. And net retention, of course, is the balance between assimilation and excretion, which varies tremendously among individuals. The efficiency of excretion is so variable. As Boyd pointed out, the metal retention disorder in the autistic children, we not only see bukus of lead, mercury, we see tin, we see tungsten. These are metal collectors. So there is a strong genetic component, and it may relate to the fact Dr. Jill James showed that they had about 1/3 less intracellular glutathione, potentially lower levels of metallothionein, the metal protective protein, nutritional status. How well is endogenous detox working? Antibiotic use markedly decreases the excretion of mercury, lifestyle, and the total toxic load. There was an interesting rat study that even showed that milk decreased the ability of rats to excrete methyl mercury. So we have to consider this total toxic load, as Boyd pointed out, because of the synergy between lead and mercury. We also have to consider other chemicals, pharmaceuticals, street drugs, and even gut-derived toxins, because this total toxic load can set one up to be much more unable to handle even a lower level of mercury. So let's talk about exposure versus retention. Exposure, a classic test, if someone thinks that they have a metal issue, a standard practitioner will draw a blood sample. But the problem with blood is the metals are cleared very rapidly, and it only shows recent or ongoing exposure, because in every toxicokinetic model of a metal, the blood pool has the very, very, very shortest half-life. So again, gone from the blood, gone from the body? No. Dr. Goyer made a very profound statement years ago that was published in Environmental Health Perspectives, which is, I'd encourage you to check that journal out, where he stated that the relationship between blood lead and post-EDTA urinary lead is nonlinear, meaning that there's arithmetic increases in blood lead associated with exponential increases in urinary EDTA lead complexes. Despite this fact, the gold standard is still blood lead, which has dropped from 40 to 20. It's now down to 10, and there is discussion of dropping it even down to 2, because even the ATSDR, the CDC, has stated that there is no safe level of lead, particularly in children, which is where the focus is on lead. Now, this is a very profound statement that everyone should have. This is a recent posting on the ATSDR website where and it just shocked me when I saw this, and with 8 classic references, they're basically saying that the EDTA provocation test, where you give EDTA and look for lead in the urine, is considered to be a reliable measure of the potentially toxic fraction of lead body burden. That is net retention. This is a hugely powerful statement in the right direction. And you really should have keep a copy of this for your records, and I do have the references if you'd like to see them. So, in my opinion, the precedent has been set, and we should assess the retention of lead and other metals, specific metals with specific agents using EDTA, DMPS, or DMSA that are currently available. And it's really important to do on the initial challenge, provocation, a pre and a post. There's 2 reasons for that. The pre will tell you, you can do it as a first morning void. It will tell you ongoing exposure, which you want to know about, because there's no sense trying to detoxify someone unless you stop the exposure. You've got a dog chasing its tail. Secondly, for legal purposes, knowing the pre and post is that's important, very important piece of information, because if you don't know the pre and post, you can't make an assumption about net retention. Unfortunately, I had to be an expert witness for a lawsuit where a firm was being sued because these women were exposed to lead there. And the doc only had the post-provocation lead levels that were quite high. And the enemy suit, was able to convince the judge by saying that lead that came out post-EDTA in these women could have been something they got into the night before. He challenged me and asked me questions like, Dr. Quig, are you aware that there's still like Cessna airplanes out there that are running on lead-containing gasoline? Well, yeah. Did these women hang around and work on those engines? No. But without that pre and post, the judgment went against the doctor because he couldn't prove net retention. Very important point. Now, the mobilization of metals is determined by 3 primary factors. 1, the relative affinity of the agent for a specific metal. 2, the mass competition among elements. in the body that have similar affinities for a particular agent. So if you have two metals that have similar affinity for, say, DMPS, the metal that's present in greatest abundance is going to be most highly bound. So mass competition. And most importantly, something that has really hit home with me in my conversations with Boyd is the competition with endogenous ligands. The divalent inorganic mercury binds to protein sulfhydryl groups at a log K of about 10 to the 40th, which is like super Velcro. It is incredibly tightly bound. Now, what do we have when we do affinity binding studies in vitro? We have a test tube, we have a buffer, we have a pH, and we have a temperature. We've got basically water, a metal, and an agent. There is no endogenous ligand to compete for. So we need to be very careful when we look at these affinity constants for the different agents, which is what I want to get into right now. These are the equilibrium constants are basically how tightly different metals will bind two complexes of DMPS. And I show K1 and K2 because DMPS forms monomers and dimers in circulation. Two molecules of DMPS attach via one of the sulfhydryl groups on each of the molecules. As a dimer, there's a slightly higher binding constant approaching that of endogenous ligands. For inorganic mercury, we get silver. Organic mercury, copper binds very well on down the line. And so, again, this is in a test tube. There was an interesting study, and many people have made a big deal about DMSA versus DMPS for organic versus inorganic mercury. But from everything that I've seen, the thousands and thousands of tests that I've seen in people that consume fish or people that have a load of amalgams, we see a very significant spill of mercury, regardless of whether it's inorganic or organic, with DMPS. Now, this is a very recent study, Clinical Toxicology 2007, where they looked at the post-DMPS, and it was oral DMPS at only 200 milligrams, followed by a 2 to 3 hour urine catch of 75 mercury-intoxicated gold miners in the Philippines. And this is a huge problem with mining for gold because of the cinnabar and the associated mercury. But what I show here is in the the levels, and that's a pretty high level, microgram per gram creatinine, of inorganic mercury, which they're primarily exposed to, but also organic mercury. After the DMPS, there's a huge increase in inorganic mercury in the urine. This is the average, or median rather, and this is a maximal value. For the organic mercury, the average was much less. There's much less exposure. However, many of the people in these villages are consuming fish from the mercury-contaminated water. So we had some individuals with organic mercury levels as high as 2,000 microgram per gram creatinine. Now, let's talk about EDTA. Boyd talked about the toxicity of an EDTA mercury complex in a test tube with ground rat brains. And many people, there are some people, I should say, that argue that EDTA is, in fact, a good agent for removing mercury from the body. And they always cite an equilibrium constant of something in the neighborhood of 21. I think Boyd said 26, depends on your experiment. So a fairly reasonable binding constant in vitro, actually higher, slightly higher than lead, which EDTA is FDA approved for, and higher than things like copper, cadmium, zinc, and on down the line. So we look at this affinity constant and we say, darn, EDTA must work pretty good for mercury. But remember, this is with no endogenous ligands present in the tube. To bring it home to you, if we look at an animal experiment where the rabbits were loaded with mercury chloride, kidneys were removed, and then they incubated slices of those kidneys at equivalent concentrations of the different chelators or metal detox agents. And what's shown here is the percent reduction in kidney slice mercury expressed as reduction in microgram per cell. Microgram DNA is essentially expression of a cell count. Significant 86% reduction by DMPS and DMSA, the dithiol compounds. D-pen, which is a monothiol, did not reach statistical significance but appeared to have some efficacy. Dithiothreatol, which if you've ever done gel electrophoresis of protein, it's that nasty, nasty, rotten egg smelling chemical in the lab. You wouldn't give it to people, but they used it because it was a thiol compound. No significant reduction with lipoic acid. And look at EDTA. Despite that high, relatively high binding constant, you've got endogenous sulfhydryl groups in these kidney cells. You've got a huge amount of metallothionein and glutathione, some of the highest concentrations of those two, the peptide and protein in the body, are in the kidneys. So no effect of EDTA on removing mercury from these slices. Now we took it a step further and did a study in real live human beings, because many people say, oh, it's a rabbit and rabbit kidneys aren't human kidneys. I don't quite buy that. We have to be careful how we extrapolate from animal studies, but that was pretty conclusive data. So what we did was we compared the slow push calcium disodium EDTA at 3 grams in 14 relatively healthy medical staff from a clinic. And what we found was that the lead excretion increased by a factor of 147, which is what we would expect with EDTA. Look at the zinc, 32 times increase. You have to be really careful with depleting zinc with EDTA. Free manganese, 15 times increase. Free iron and cadmium, and even antimony. Absolutely no increase in urinary mercury or fecal mercury with this high dose of EDTA, which is consistent with the kidney slice study and not consistent with the in vitro stability constant. So I really want to put that to rest based on facts. Now, it's really important to realize that with this pharmacological detoxification, with the agents that are currently available, there are some real limitations, huge limitations. One, the agents are restricted to the extracellular aqueous compartment. They do not get into the cells, and they're water soluble. Hence, they do not appreciably cross a healthy blood-brain barrier. So what happens is they're pulling metals that have either remained in the extracellular space or been pushed into the extracellular space by endogenous processes. So by pulling the metals from the extracellular matrix, you create a concentration gradient because the metals are higher in the cells than they are in the blood. And so each time you go through with an agent, you're pulling away and causing this kind of pull-push phenomena where the intracellular detox wakes up a bit, especially as you start to pull these things, recreates that concentration gradient so that when you come back in the second time, you're going to have available in the extracellular space, which is why it's critical to have time, a pulsing sort of protocol, as opposed to just pounding away from day after day after day. You're going to cause, if you do that, you're going to more likely than not generate an allergic response or sensitivity to the agent, particularly DMPS or DMSA. And also, you're going to get much less bang for your buck because that concentration gradient hasn't been allowed to work. And you're also likely to deplete essential minerals, which are so important in the detoxification process.
What is that time period?
I will talk about that in a minute. Yeah. Typically about 10 days. Now, there is a phenomena that we found out the hard way in working with autistic children, which are notorious for having absolutely atrocious dysbiosis. Yeast, fungal overgrowth, bacterial overgrowth, even parasites. And we found out the hard way that if one introduces these thiol-containing compounds, N-acetylcysteine, alpha-lipoic acid, or DMSA, markedly exacerbated not only the GI symptoms in these young children, but also their stimming behavior and their aberrant neurological behaviors. And apparently, based upon looking at fecal bacteria and fungus before and after using these agents, there's actually an increase in the growth of these undesirable enteropathogens. Dr. Haley had published on his website the fact that there are certain bacteria. An example of a common one would be Citrobacter frundi, which is a urease-positive bacteria that produces hydrogen sulfide and ammonia from cysteine. So one has to be very careful in using these oral agents in people, and especially these autistic children, that have dysbiosis. So the point is to assess and clean up the gut if you're going to use the oral route with this type of agents. To get around that, there was an urgent need to do something about the current metal load in these children, because there's this terrible vicious cycle between the metal retention, which is markedly immunosuppressive to both humoral and cellular immune-mediated systems, knocks out natural killer cell activity and number, and phagocytosis. And so what some docs wanted to do was, A, provocations with DMSA without throwing the DMSA into this inferno of a dysbiotic gut, and secondly, possibly even use the suppository route, bypassing the gut, in effort to help decrease the metal burden so that one has a fighting chance in this compromised immune system to get rid of the enteropathogens. So we did a study, and it's actually up to 10 now, where we looked at DMSA suppositories given to 3- and 4-year-old little kids who had never been touched with any kind of metal detox agent, and this was 5, and gave the suppositories at 20 milligram per kilogram, collected urine for just 6 hours. And much to my surprise, what's shown here is the pre and the post lead for each child. I was very pleasantly surprised to see that with a 6-hour collection rectally, that we would get this kind of result for a provocation, showing estimating net retention. And this poor guy is just loaded with lead. And I really want to emphasize that while there's no doubt that the mercury and the thimerosal is a huge issue in these children, we see tons of lead coming out of these children. People like Dr. Usman, who have been using methods to get rid of the lead, seem to find that when you get the lead out of a child like this, then you're going to start seeing the mercury come out. So again, we have this mass competition phenomenon going on. Same thing with mercury with the suppositories, pre and post. Every child showed a significant net retention with the suppositories. Similar studies have been done with suppositories of DMPS. Again, a 6-hour collection sufficed. Now, I want to talk about some other topics related to mercury detoxification, the first of which will be selenium. Now, this is a post-DMPS urine mercury result of 420 micrograms mercury per gram creatinine in a high-level executive CEO woman. So that's a very high level. Doc really didn't have any idea of the source of exposure. So that was the first DMPS provocation. He then put the patient, or maybe the patient didn't tolerate DMPS or didn't want to use DMPS or DMSA, so he put the patient on a very high dose, 750 micrograms of selenium a day for 5 months. And after that 5 months, you can see, looking at the red cell selenium concentration, it was very high. Now, that's all that was done, was the selenium. He went back and re-challenged the same way with DMPS, and only 37 micrograms of mercury came out. 34 micrograms per gram creatinine. So does that mean that the selenium got rid of the mercury in the body? No. There's numerous studies that clearly show a very stable and very tight adduct form between mercury and selenium, mercury and cadmium. It's a 1-to-1 adduct. They found this complex in the brains of deceased dentists in high concentrations in certain parts of the brain. Interestingly, there's no evidence of histopathological damage in the vicinity of that mercury-selenium complex. Now that's histopathological. That doesn't necessarily address all the very, very important biochemical reactions, the neurotransmitter functions that are going on. So we have selenium neutralizing mercury by binding to it, removing its charge, and however, that decreases the ability to remove that mercury from the body. You neutralize it, but it's locked up in the body. So my take-home point is that if you choose to leave the mercury in the body and tie it up, high-dose selenium might be a way to go. Most people would like to get the mercury out of the body because there's too many unknowns. And just looking at histopathological damage in deceased dentists isn't an ideal way to assume that it's safe. So avoid high-dose selenium when trying to remove mercury. Obviously, you need selenium for things like glutathione peroxidase, especially in the thyroid gland, which is very sensitive to mercury, but for many other important antioxidant type reactions. Now, what about IV reduced glutathione, push versus drip? There's lots of hallway talk about, well, I drip my glutathione in and I get better results. Well, I push my glutathione, as Dr. Perlmutter advocates, with, what is it, Parkinson's? Or Alzheimer's? Parkinson's, I believe, yeah. Well, when we think about this, we know that, and we've talked about glutathione conjugating mercury, methylmercury, to a lesser extent, lead and cadmium. And the fact of the matter is that the normal blood levels or serum levels of reduced glutathione are very low, only about 10 micromolar. It's about 10 millimolar in the cells, 1,000 times higher in the cells. And at the proximal tubules, there is very efficient absorption, uptake of glutathione. And this requires gamma-glutamyl transferase as well as some dipeptidase enzymatic activity. And this is only present on cells in the kidney, deep in the lung, the liver, and in the intestine. So what we have is the potential for uptake of mercury or metal or some other xenobiotic bound to glutathione, high uptake by the kidneys if we put it in slowly. And this has been demonstrated in rat studies where they found very high urinary glutathione mercury complexes excreted in the urine and decreased renal retention of glutathione mercury complexes when they used a chemical inhibitor of that gamma-glutamyl transferase, so blocking the ability of the kidney to take up that glutathione toxin complex. If the ratio of mercury to glutathione was only 1 to 2, which is kind of unphysiological, there was actually increased renal toxicity because the relatively small amount of glutathione going through did not saturate that uptake system, and you actually enrich the kidneys with mercury and cadmium. Whereas if you go to a much higher ratio of glutathione, you can actually protect the kidneys. So based upon this animal experiment, which no doubt was pushing the envelope to demonstrate the phenomena, it is my opinion that one should use a bolus push of glutathione versus a slow drip so that you saturate that glutathione uptake process at the kidneys, tie it up with some glutathione bound to mercury or lead, and then the bulk of the rest of that infused glutathione will slip past that uptake mechanism, and you won't clog up the kidneys. Now, the big study, Chlorella. Everyone always talks about Chlorella. I should say a lot of people talk about Chlorella and its wonderful ability to detoxify mercury. There's not a single study, to my knowledge, that was done in a mammalian system to demonstrate this phenomena. There are some studies with respect to metal removal. There are some interesting old studies from the Japanese literature that shows that Chlorella had very, very important growth stimulating and wound healing effects in both animals and emaciated Chinese prisoners. Imagine that. Give a source, an alternative source of protein, dried Chlorella, and their wounds heal better. Okay? But that's it. So that's great. It's an alternative source of protein. Now, since there were no studies to demonstrate that dead Chlorella, which one purchases in a plastic bottle, does have the capacity to remove mercury, we wanted to do a study in real-life human beings. And we used a green single-celled Chlorella. And it's known that live Chlorella can take up divalent metals from water, ponds. You can make a column out of live, slimy green algae live, pass contaminated water through it, and have clean water come out. Just like you can make a column out of Boyd's compound. Pass a mercury solution, a concentrated solution through it, and no mercury comes out. But in this case, it's live algae. And there's lots of studies that show that you can use live algae to clean up ponds and drinking water. Okay, I already talked about the high protein and chlorophyll content. So we wanted to study this phenomena and see if, in fact, in a controlled manner, we gave high doses of dead Chlorella to some students. Students are great for this sort of thing. They're always looking for extra credit. Whether, in fact, it would enhance their mercury excretion. And before doing the study, because of the potential for live Chlorella to take up toxic metals, it depends on where they're grown. So you always want to know where this stuff came from, so we analyzed the Chlorella, contained insignificant amounts of the 4 primary toxic metals. So what we did was an IRB-approved study at Southwest College of Naturopathic Medicine. 8 volunteers, students, each with at least 6 amalgams, so they're mercury positive controlled, basically. They had no metal detox or dental work within the past 3 months, and they had to have regular bowel movements of 1 to 2 a day. Okay, perfect. They were to consume no fish 5 days prior to the basal specimen collections or during the trial. We didn't want to cloud it with the methylmercury issue. And we looked at 24-hour urine mercury output, all metals as a matter of fact, and fecal specimens collected prior to and after 3 and 7 days of supplementation of 8 to 10 grams of dead Chlorella a day in divided doses. So mercury positive humans, 8 to 10 grams of Chlorella a day, looking at multiple time points. Short-term study. Here's the results of the fecal mercury excretion. Some say that, okay, well, it's dead. It's going to bind mercury in the GI tract and block enterohepatic reuptake and enhance fecal mercury excretion. Compared to baseline, there was absolutely no increase in fecal mercury in these people that had a significant number of amalgams. When we looked at the urine, it was kind of interesting. Compared to baseline, there appeared to be somewhat of a trend. However, the variability, again, we're only looking at 8 subjects here. So there appeared to be a trend, but very small increase in the urinary mercury output. Now, when we look at individual patients over time, and each patient is represented by a color, you can see that compared to baseline, most of the subjects had very little to no increase in urinary mercury output. There were 2 patients that appeared to have a sharp increase, particularly after the 8th day, particularly this individual. And obviously, eight subjects is insufficient to draw a strong conclusion, but one possibility is that this individual might have been a vegetarian and may have been lacking sorely in the intake of cysteine-containing proteins, and it could be that the chlorella at 10 grams a day was providing increased cysteine to increase intracellular glutathione. The most common side effects, which were noted in all 8 individuals, were constipation, gas, bloating, diarrhea, nausea, and headache. One patient, or subject rather, even had urinary incontinence. Could be purely coincidental, I would assume. So, there was absolutely no effect of 8 to 10 grams of chlorella a day on the fecal excretion of mercury in subjects with an average intestinal mercury exposure. There were undesirable GI side effects at this dose of chlorella, and 2 of the subjects exhibited a trend for slightly increased urinary mercury excretion, and we can't tell for sure. It's too small of a study. So my take-home thoughts are that dental amalgams in situ contribute significantly to global environmental mercury pollution. Use provocative urine challenge to assess pre and post to assess and monitor the net retention of mercury and other metals, and consider the glycine phenomena. Selenium should be given simply to support essential selenoproteins, which are about 9, versus mercury neutralization. And live chlorella is good in ponds. And thank you very much for your attention.